In this episode, we are going to take the RNN we created in the last episode to do translation from English to Italian, and we are going to add the attention mechanism on top of it to improve its performance. Now, most of what we're going to look at comes from the original seminal paper by Bahdanau et al., Natural Machine Translation by Jointly Learning to Align and Translate. Again, this was the first paper that showed how a mechanism such as attention can be used to improve the performance of a neural network in machine translation. Incidentally, they didn't call this an attention mechanism back then. It was actually called an alignment mechanism, but today everybody calls it attention. From their architecture, probably the most important thing to point out is that the encoder they're using is pretty much the same that we had in our previous episode. It's a bidirectional RNN, and then they use the outputs from that encoder to calculate the attention weights using a formula which I think is in the appendix actually. There it is. This is their alignment model, which again we would call an attention model. And this is what we are going to implement. So I've already run the majority of this notebook because loading the dataset and creating data loaders, batches, this is identical to what we did before, so we don't want to waste time on that. So let's look at the attention mechanism. Here is the graphical representation of what we want to implement in our attention mechanism. And this is the actual implementation of this image over here. So let's take it step by step. First of all, we have a linear layer which takes the hidden size times 2 and projects it into a hidden size times 2 without a bias. So this is essentially, you could imagine, the first or the input layer of this simple attention mechanism. And the reason why it's hidden size times 2 is because the inputs to this attention mechanism are the decoder current state for the current word that we are trying to translate, and then the encoder input word that we want to calculate the attention for. So this is why it's hidden size times 2. Now, this multi-layer perceptron needs to return an attention weight. So this is why we add this output layer, which takes the hidden size times 2 and projects it into just one output neuron. So it will give us this attention score. And what does this attention mean? This tells the model, while it is translating or trying to translate the current word, which is represented by this hidden state here in the decoder, how much attention it should pay to the input word at index 0, input word at index 1, and so on. So these hidden states from the encoder, that's what they are carrying. Now, how does it do this? So the forward pass is pretty simple. There is a little bit of tensors kung fu to get things into the right shape, but essentially what we're doing here, we're taking the encoder hidden state at the current step for the word that we want to translate now and that we want to output now, and we're repeating that. So we are copying that over as many times as the words that we have in the input that come from the encoder outputs. So we're basically taking this term here, d minus 1, because here we are calculating C0, so this is the context for the first word, so this is the hidden state of the current decoder, and we are copying it over 1, 2, and 3 times in this case. And that's all that this repeat is doing. And then we are concatenating this with the encoder output. So we are then concatenating that with H0, with H1, and so on. So why are we doing all of this? Remember, when you look at this bit here is the multi-layer perceptron. This is not a separate one. This is the same, and we need to pass all of these tuples or couples that we've created, or pairs, that we've created through this. And we could do it with a for loop, but it would be incredibly inefficient. So instead, we are copying this over, we are concatenating it with the hidden states from the encoder. So we've basically created a batch. So we can pass that batch with matrix operation. So this combined batch through the first layer, this attention layer that we've got here. Obviously, we apply a activation function, in this case stun h. Remember, we really want to apply an activation function. If we remove that activation function, we essentially make this a linear layer and we won't learn enough. Then we take that output and we pass it through the other learnable layer, which is going to return the attention score. So that's where we are. All of this needs to be passed through a softmax so that the scores that we have here, they will sum up to 1 when they come out of the softmax. And this is much better because it allows the model to learn in a stable way what to pay attention to. Now, once we've computed these attention weights, we can create the context vector. And the context vector, we simply take a weighted sum. We now have the weights, a weighted sum of each encoder hidden state with its associated weight, and then we return a context. Now, again, what's the idea? The idea is that the model, this model here, should learn where to pay attention to. And so if this particular word is not important in the input for the current word that we're trying to translate, this attention weight should be pretty low, which means it will not be much represented in this weighted sum. Conversely, if, for example, the third word in our input was important for whatever we're trying to translate now, this attention weight will be really high. So this hidden state from that second word will be more represented or more heavily represented in the context. And so the decoder at that particular time step will be able to make use of that information. So this is what we are trying to do. We want to add the context to the decoder so that it can be used. So this means that when the decoder for the current step, so this is the first step of the decoder, it will have one input, which is the start of token, and that will be embedded exactly as before, but we're going to concatenate a context for that particular input. And the way we're going to calculate this context is by using all of the encoder hidden states, which obviously map to input words in the original sentence, combined with the attention scores that the attention mechanism has learned. So we create this context and we concatenate it with the input. So obviously now the decoder will have much more information to produce the next token, and so on. So for every input or for every step in the decoder, we will create a completely different context with completely different attention weights that will make it focus on the specific words that matter. So how do we do this in practice? Our encoder stays exactly the same. It's a bidirectional RNN, and we return all of the encoder outputs and all of the hidden and cell states. Go back to the previous video if you want to look at this in more detail. What changes is the decoder. So here we initialize the attention class that we created by passing it the hidden size. So now we have these additional learnable parameters in the decoder. I also have an attention matrix. Don't get confused with it. You can remove the attention matrix. I just have it there because I want to be able to collect the attention weights so that we can take a look at those later and we can plot them to see what the model is actually learning. But all the rest stays the same. The only other difference with the previous decoder this time is that the input of the decoder is not just the embed size, but obviously because we are concatenating the context, the size of the context is the hidden size, so the input will be much bigger and it needs to take into account the hidden size coming back from the context. So essentially, this is the embedding size and this is the hidden size that's been produced by that weighted sum in the attention mechanism when we do the weighted sum. And that's it. Now, in terms of the forward pass, we do the embedding of the input as usual, but then we are also taking the encoder outputs as an additional parameter. We are passing these to the attention mechanism together with the current hidden state. And sorry, I keep messing this up. And these will return the context vector for the current word being translated. You can ignore this, and then we concatenate the input with this context vector. We have the LSTM input, we pass it to our LSTM, and this is exactly the same forward pass as before. So these are all the changes that we need to make to take into account the context. Now let's instantiate this, and we are gonna keep it exactly the same size as before. Obviously the decoder is going to be bigger because we have an additional set of parameters for the attention mechanism. Now, how does inference work for translation? Exactly the same as before, again with the difference that this time we cannot discard all of the previous hidden states and we have to carry them along to the decoder. So that's what's happening here. If you go back in the previous translation method, we were ignoring that, but now we're not ignoring it anymore. We're collecting it and we are directly passing it to the decoder when we do our forward pass. And when I look at this, I think everything else is the same. So as usual, we have a sample sentence and we run it through this and we have 15 random words because we haven't trained the model and no end of sentence is being produced. And so we get 15 random words. Before we train it, I want to show you the attention matrix that's been generated for that sentence by the untrained model. So the plot attention takes the attention matrix, the input sentence and the translated sentence and plots it like this. So you can see the output sentence here and the input sentence there. And obviously this is a random attention matrix the model hasn't learned yet. Now, you can train this model for 10 epochs or 15 epochs. Everything else is the same in the training loop, other than obviously using the encoder output and passing the encoder output to the decoder, but everything is pretty much the same. I am not going to train this model because I've already trained it and I have uploaded the encoder and decoders to my Google Drive, and you can download them if you don't want to waste time training this model. So we can just get those and load them into our models. So all the keys matched successfully. Let us go in and see how it translates this sentence. È una brava insegnante. Now, this is a good translation, perfect translation, and more importantly, because she's a female, this ends in an A, which, if you recall, our previous model was struggling with. Let's take a look at the attention matrix for that sentence. So this attention matrix looks like it makes sense. So when it was translating it was focusing mostly on is, which is indeed the word that translates that. Una, it was focusing mostly on a, which again makes sense because that's the translation. But it was also focusing on teacher. Probably it needs to focus on that because it's learned that this word might tell it something about the gender. It doesn't in this case. It should have probably focused on this, but it is still able to translate. And that's the same for brava. Brava is matching good and teacher, and it's not paying attention to anything else. And insegnante is paying attention to teacher, which is obviously really, really good. Now let's try a different sentence. Let's try this. Tom likes hot chocolate. A Tom piace la cioccolata calda. And if we go down here, let's see what this has done. I have not looked at this before myself. So what do we see here? Chocolate relates very much with chocolate, and calda is paying attention, a lot of attention to chocolate. Now that does make sense because in order to know whether calda should be calda or caldo, it needs to know the word it refers to for the gender. So this makes a lot of sense. La is related to hot and chocolate, and it does make sense. So la is the article the, but it doesn't exist in the original sentence because in English you don't say Tom likes the hot chocolate, but in Italian you need it, and this has learned that it needs it, and it's learned to pay attention to hot and chocolate to choose the right one, because there are different versions of the article depending on the gender. So this is really good. Something else that's interesting, likes, obviously when it's producing piace, it's focusing on likes, which is the verb that translates that, but it's also, when it's producing the A token, it's also focusing on likes. This does make a lot of sense. The Italian sentence has a completely different grammar and structure, and this a is very related to likes because something pleases me. So this basically, the translation in Italian literally is to Tom it pleases hot chocolate. So likes is very related, or you need to pay attention to that. So I'll just stop here. I can probably go on for ages talking about this attention matrix and how it's learning to capture information from the input. But there you have it. We've implemented something that actually works and makes a lot of sense. Actually, before we go, I wanted to show you very quickly the attention mechanism as it is described in this paper. So it looks different from what we've done, but it is pretty much the same. It is just that in this paper, it's described with matrix multiplications. But if you look at it, we have the HJ as input, and these are the hidden states from the encoder. And indeed, our attention mechanism has hidden states from the encoder. And then it's got the hidden state, the current hidden state from the decoder, which it calls S, and I call D because it's for the decoder, but also you can look at that here. Maybe it makes more sense. So the inputs are pretty much the same for that perceptron. And now you have the first layer. And here, instead of having a layer, you have the two-weight matrices that are multiplied with the decoder hidden state and the encoder hidden state, and then added together. Instead, what we're doing here is pretty much the same. We have a linear layer, one linear layer of double size. So we're basically putting these two matrices together and then putting these two inputs together and doing a matrix multiplication. If you remember, that's exactly what a linear layer does. The only reason they are splitting it here, I think, is because they can optimize this, and this calculation, they can only do it one and reuse it for every time step, because the encoder hidden states do not change, so they can optimize this bit here. Then we have a tonnage, which we have here. And then we have the application of this second layer V, which is exactly what we have here. And again, this layer VA, this matrix, you can see that it's just N, because this is just projecting from this size, which would be N, into 1. Whereas the other matrices are hidden and hidden. So N times N, as you can see here.